Thanks, Nick. So, as Elaine mentioned, I'll be talking briefly about a flash detection where we followed up with MUSE data. And specifically, we were looking at a galaxy group at intermediate redshift. So just very briefly, we sometimes refer to galaxies as island universes, but this terminology isn't quite correct in the sense that galaxies aren't these isolated or self-contained systems. And this becomes abundantly clear when we look at galaxies that are interacting or in denser environments. And shown here is the M81 triplet. So we see these interactions most clearly in the H1. We see these beautiful filamentary gas structures extending between the galaxies. But much of our knowledge is still limited currently to the local universe. But if we want a complete picture of how galaxies have formed and evolved over time, we will need to move to higher redshift. So as Elaine talked about, the FLASH team is aiming to probe a redshift range of about 0.4 to 1.0 using H1 absorption studies. And this redshift range covers about 4 billion years in look-back time. So not only are we attempting to constrain the H1 mass density in this region, but we also, the samples, our detections allow us to study the distribution of H1 in galaxies at this redshift range, which is still largely unexplored. So the detection my work during my honours year focused on was along the line of sight to Park 1610-77, and it was found at redshift 0.45, and we see this right here on the screen. We find actually there are two components, and these are roughly 45 kilometers per second apart, and this is already hinting at perhaps more complex kinematics. So the quasar and its surrounding region was actually observed previously, and there were 4 galaxy-like objects found. They've been labeled here A, B, C, and D in the left image, and object D is only visible after a PSF subtraction of the quasar, and this is clearest in the R-band image on the bottom left. Galaxies A and B have been spectroscopically observed, and their redshifts are consistent with the redshifts of the absorbing gas. So the spectrum of the quasar itself appears to be highly reddened, and this suggests the possibility of some sort of intervening object. Additionally, the authors 2 decades prior noted that there was an unknown absorption feature around 8,500 angstroms, and this is something I'll return to later. So there are 2 main questions we want to answer. And so the first is, which galaxy or galaxies are actually associated with our neutral gas? And second, what is the relationship between this gas and its surrounding galaxies? So to do this, we need more data, and we turn to the MUSE instrument, which gives us a wealth of data to work with. So first, we will revisit our quasar spectrum and look at those unidentified lines to see if they are useful. Second, we can identify galaxies associated with our absorbing gas in a 1 arc-minute squared field of view. And finally, we want to analyze the properties of some of these galaxies. So firstly, this is the spectrum of the quasar from MUSE, and it is really quite beautiful. You might notice that there are a bunch of absorption lines labeled in green. So these actually belong to another metal system at redshift 1.62, but this isn't associated with our neutral gas. And then there are these lines around 5,700 and 8,500 angstroms. And these turn out to be calcium-2 H and K and Na1D1D2 at the same redshift as our neutral gas. If we look at the Na1D line on the right, we see that we may require multiple components. We find that when we fit these components, that the first component actually matches very well with our ASKAP detection. It's at redshift 0.4503. This isn't particularly surprising because calcium-2 and Na1 are known to be quite good traces of relatively cold neutral gas because their ionization values are so low. But this is still quite a neat result. Additionally, we find that there's actually a second component not seen in ASKAP, possibly due to a high spin temperature or lower column density. And this component is about 180 kilometers per second redshifted from the first. So already just from a single spectrum, we've learned something new about our neutral gas system. So if we take a narrowband image, there's something happening on this. If we take a narrowband around O2 of the MUSE field, we find 4 galaxies. We see galaxies A and B again at the center of the field, but we also find more than 100 kiloparsecs from the QSO galaxies X and Y. Pardon the relatively poor naming convention. We note that
yep, your video is frozen. There you go. I shut off your video. Continue.
Yep. Okay. So we find that these galaxies are aligned in such a way that there appears to be some sort of filamentary structure stretching from southwest to northeast. And this is quite interesting. So if we use source finding on the entire field, we find that it is indeed only these 4 galaxies that are associated with the gas. That is, they are at similar redshifts to our neutral gas found with ASKAP. We find that object C from before is only a foreground M-type star, and we find object D is a background galaxy. I've also labeled 3 other galaxies here with numbers 1, 2, and 3, and these are at slightly lower redshift, and they possibly belong to a larger scale structure. So let's move on to some basic properties. And the first we will focus on is just a redshift and a projected distance or impact parameter. So we find that not only are galaxies X and Y far in terms of velocity, in terms of impact parameter to the gas, but they're also far in velocity space. Galaxy X is about 300 kilometers per second from our gas, and Galaxy Y is about 750. If we look at galaxies A and B on the right in a zoomed in image, we find that galaxy A is closest in terms of impact parameter, but galaxy B is closest in terms of velocity. At this stage, it appears that the gas is most likely attributed to galaxies A and or B. So one crucial thing MUSE allows us to do is then to compare the ionized and neutral gas kinematics. So in this plot here, I've plotted the ASKAP spectrum in black, with its 2 velocity components with the blue and green dashed lines. The CA2 spectrum is in grey, and its second component, the red one from before, is plotted with a red dashed line. The galaxies are plotted using various symbols according to their redshift and impact parameter to the gas. This has all been centered around the systemic redshift of galaxy B. At the position of galaxy B, which is a circle, there's a horizontal bar, and this is the extent of its ionized gas rotation. So now we can translate this to a 2D plot. But first, if we look at the ionized gas emission for all 4 of these galaxies, A, B, X, and Y, from top to bottom, we find that galaxy B really has quite strong emission lines, and its star formation rate after extinction correction is close to 8 solar masses per year. But from its emission lines, we can also gain understanding of how the ionized gas is rotating, and this is what we see on the right. Where there's clearly resolved rotation. For galaxy A, because it's compact and because the signal to noise of the emission is quite low, I've only plotted here a single value corresponding to its systemic redshift. At the position of the quasar, there are 3 vertical stripes. The blue and white stripes are the ASKAP H1 components and radio data, and the red stripe comes from the second component from fitting the metal lines. So this plot is very useful because immediately we note that the red component detected with MUSE in the metal lines can be attributed to an extension of the rotating disk of galaxy B. It could be part of the outer disk of galaxy B. But more curiously, we find that there are 2 components, that is the radio components in the H1 that do not align with this rotation. So we need another explanation for the origin of these components. And the most likely explanation I arrived to was that these components arise from extragalactic gas clouds. So on the left is actually something from the Wallaby survey, where they found these clouds of gas outside the optical extent of galaxies in an interacting system consisting of a group of galaxies. So we believe that these components we see with ASKAP for Park 1610 is essentially some sort of intermediate redshift analog of what was found with Wallaby. So in summary, this combination of ASKAP and a follow-up with MUSE is extremely powerful as it gives us the ability to study the relationship between the ionized and neutral gas in a system and at a redshift range that is still largely unexplored. In the future, we expect around 1,000 detections with ASKAP. We may not expect 1,000 MUSE cubes, but follow-up optical spectroscopy will allow us to, I guess, further study the relationship between gas and galaxies. Thanks.